Okay, so let's continue our discussion on the metric topology. So this is where we left off last time, I can remember. So we talked about spaces being metrizable if we can put a metric on them that gives the topology that we're interested in. And so we were looking at topologies given on Rn. So we saw that on Rn, there's a whole bunch of different norms that give different metric topologies. Well, maybe different, but they don't. They all give the same one. And the dilemma that shows us how to kind of easily compare metric topologies is this lemma here. So that one topology is finer than another if we can always fit in a ball in the finer topology inside a ball of the other topology. Okay, and so with that, we can then prove the following theorem that that the topology given by the Euclidean metric, remember that's where normal Pythagorean distance gives us the topology given by the square metric, which is kind of like the sup norm, is the same as the product topology. Okay, so that's where we're at. And so basically, what we're going to do is use that lemma then to prove that that space here. And the important result that gives that for us is the following, that if we have 2 points, 2 elements of Rn, then the square norm, the square distance or the square metric, the distance given by there is always less than or equal to the Euclidean distance, and that's less than or equal to square root of n times the square metric. Okay, and let's just, before we prove that, let's just pause for a minute to see why that means then that these 2 metrics have to be the same. So basically it's saying then that in that case, a ball in the square metric going to be contained within the ball. Right? Because if anything is epsilon away in the Pythagorean distance normal way, then it's for sure going to be epsilon away in the square norm way. And if anything is epsilon over square root of n away in the square norm, it's definitely going to be epsilon away in the distance norm. And Why is this so? Well, if we just look at what the distance norm is, right? What's the distance norm? That's the square root of x1 minus y1 squared plus x2 minus y2 squared plus, let's say, xi minus yi squared plus all up to xn minus yn squared. So remember, this is the soup norm, but we're in a finite space. We've only got finite dimensions, so the soup is the same as the max. So at some coordinate, it actually attains its maximum. So let's just say it's the ith one. Well, if there's the max there, then if all of these were 0, you would get exactly the square norm. But the fact that we've got other things, that we could have other things here, means that this is actually going to be greater than or equal to that. And, well, how can we maximize this? Well, we can maximize if all the other x sub j minus y sub j's are the same, they all reach the max at the same time, in which case down here we're going to get n, we're going to get n times of these. We pull that out, we get the square root of n, and we're left with just the square norm there. Okay. And you can actually do a similar proof for all the p norms. You can get, with the other distances that come from the other norms, you can set up a similar sort of inequality, and you get it. So all the balls are within the other. For example, I think I showed you this picture before. If we just look at R2, what do balls look like in R2? So here is the 2 norm is just a circle. The square norm is just a square. And for example, the 1 norm is this square here. And then all the other norms just fit. So this is at 1, this is at 2, this is at infinity. All the other norm, the balls fit between those things there. You can set up a similar thing there. Okay. So that shows that the Euclidean metric and the square metric give the same topology. And why is it the same as the product topology? So let's just say that the square metric, gives the product topology. Why is that? So let's start off with a typical basis element in the product topology. That's going to look like A1, B1 cross A2 to B2 cross all the way up to AN B. So where these, of course, are intervals. So remember, we're using crosses for our product. So here's our B. So let's say we've got some element of this basis element of the product topology. So we've got to somehow fit this in with the other topology. So we've got to fit it in with balls. So here we've got intervals. What we want is balls. So, so for each I, there is a epsilon I greater than 0, such that xi minus epsilon I to xi plus epsilon I is contained within ai bi. So at each coordinate, we've got a ball fitting inside our interval. And that's basically the main trick. And so let epsilon equal the minimum of all these epsilon i's. Then what do we got? Then the ball in the square metric centered at x with radius epsilon is going to be contained within B. Okay, because we want to make sure the maximum distance, we're using the sup norm, well, by making sure that epsilon is the minimum of all these, we're ensuring that the greatest distance lies within epsilon, will lie within that V there. Okay, so what does this tell us? This tells us that the P metric topology is finer than the product topology. Okay, this is just the standard trick. As long as you can get any if you can get the basis element of one topology inside the basis element of another topology, that tells you then you've got to find a topology. But then you just got to go the other direction. So we've got to do the converse thing. So now we've got to show that a product topology can be put inside a product topology basis element can be put inside that's a row, actually, a row metric basis element. So what does a row metric topology element look like? It looks like a ball in the row metric centered around X with radius epsilon. So that's a but this is not only a basis element in the square metric topology, it's also a basis element in the product topology. So it is both. So that means the product topology is finer than the square metric topology, and that finishes it off. Okay, so that finishes our discussion for Rn for the moment. Interesting thing, of course, happens is when we let our index set be infinite. So, of course, straight away we start getting nervous when we start talking about infinite things. So, for example, let J be omega. So in that case, R omega is going to be, R to the omega is going to be basically the same as a set of sequences. Okay. Well, putting a metric on that can be kind of hard. Because, for example, sequences don't need to be bounded. Right? If it's an unbounded sequence, then you can't really do stuff with the square metric. Definitely, the sum of the squares, the square root of it, it's even worse, right? Because for that to be true, it definitely has to be going to 0, right? The tail. So what we do is, but we know how to handle stuff that gets unbounded. We just put in a bounded metric. And so we have what's called the uniform metric. Right, so what we do is we let our metric be the soup of the standard bounded metrics. And remember, the standard bounded metric is defined to be either the distance between x and y or 1, whichever is the smaller. So when we do that, everything is bounded, and so things are well defined. So we call this metric the uniform metric. And the topology it induces is called the uniform topology. Okay? So this is just a topology in which all distances are going to be defined, and so it guarantees that you're going to have some kind of topology on your set. Okay. And so here is the result that we have. That it's finer than the product topology, and it's coarser than the box topology, and that these topologies are all different if we have an infinite index set. And of course, simply know for finite that the product topology is the same as the box topology, then the uniform topology has to be the same. It gets squeezed in between those two things. So what does it say? So it's saying that the uniform topology has more open sets. So anything that's open in the product topology is also open in the uniform topology. The uniform topology is going to have more open sets, and the box topology is going to be even more than the uniform topology. Before we start proving this, we're looking at this topology here. We still want to use the other norms, like the Euclidean norm and the soup norm. And the way you've got to do that, of course, is that you don't look at the whole product space of R omega. You look at some subspace. So, for example, if you want to use the square norm, that soup norm, then you've got to look at the space of bounded sequences. If you want to have a look at stuff which is, say, bounded, exists in the one norm, well, what's the one norm? Well, the one norm is just the sum of the absolute value of the elements. So that's basically the set of absolutely convergent sequences. So these are important analysis thing. So even though so the other topologies are still important when you get to infinite spaces. So I don't want you to forget that. Okay, so let's prove this theorem. So it's the same strategy that we used before. So we start off with something, and we show that it's we start off with an open set in one topology and show that it's open in the other. So let's show that it's finer than the product topology. And to do that, of course, all we need to do is show that any set that is open in the product topology is also open in the uniform topology. So let's start off with some basis element of product topology. And some arbitrary element of that open set in the product topology. So what we're going to do is we're going to show that there's an open set in the uniform topology which contains X. So what does it mean that it's a basis element of the product topology? That means that there's only finitely many sequences, many indices. Let's call them alpha 1, alpha n, such that U alpha I is not R. Okay, so we've got to find, so remember this is a basis element of the product topology. That means most of the things are actually, most of the sets are actually R itself. There's only a finitely many that are actually smaller than R, that are open sets in R. Let those be the indices for them right there. Since it's a finitely many, that makes it easy to deal with. So for each I, what do we got to do? We've got to choose an epsilon I greater than 0 such that the ball in the standard bounded metric on D, X alpha I, epsilon I, is contained in U alpha I. No. So this is in each component.
Right. Okay.
Right, because rho bar is for the whole product, D bar is for each component. So we're definitely just sticking to one component. And since it's the product topology, it's very easy, right? Because there's only finitely many things where everywhere else it's the whole R. So of course, whatever we choose is going to be, whatever set we choose is going to be within that. We only have to worry about the small stuff. And there's only finitely many small things. And again, we let epsilon equal the minimum of the epsilon i's. And so since there's only finitely many epsilon i's, epsilon, the minimum is guaranteed to be greater than 0. So of course it fails when you take an infinite number. Right, so but then we look at the ball in rho bar around x of epsilon, and that's going to be contained within our basis element. By choosing it to be epsilon, it's guaranteed to be within each of the u alpha i's, which are potential problems, because they're the small stuff. Everything else is the whole R, so of course it's going to be contained within there. Okay. Next, we've got to show that it's coarser than the box. i.e., we've got to show that the box topology is finer than a uniform topology. So that means instead of the inclusion going this way, we've got to go the inclusion going the other way. Well, it contains this box neighborhood. So this uniform topology contains this. So this is a uniform topology. Basis element contains this box topology. And so this shows that the box topology is finer than the uniform topology.
Is there a problem if you try to use epsilon instead of epsilon over 2?
Sorry?
In the
other direction?
In the product of open intervals, why are we using epsilon over 2 there?
So why are we using epsilon over 2? So if y is an element of u, then the distance between x alpha and y alpha is going to be less than epsilon on 2. That's true for all alpha. So hence, since these are true for all alpha, then if we take the sup of them, then rho x alpha y alpha is going to be less than or equal to epsilon on 2. So we've got to use an epsilon which is small. We've got to use a radius which is smaller than this. And the fact that they're different, that's a homework exercise. So why you can't go the other direction. Okay, so this shows that, so what we've found is that our omega is a space that we can put some metric on it. And we can turn up with this uniform topology. So what we haven't shown is that it's metrizable in either the box or the uniform topology. We've just shown that it's metrizable in this uniform topology. So what happens? Then it turns out that the product topology is metrizable, but the box topology is not. And in fact, the product topology is only metrizable if we have a countably infinite index set. So if we have a look at the product topology on R to the R, for example, then that is not metrizable. So here is a metric that gives us the product topology. So again, we're taking the standard bounded metric on R, and now we're going to define a metric by looking at the sup of the standard bounded metric divided by I. So notice that this is different from the uniform metric, where we're just looking at the sup for all I. So this is enough to ensure that we have the product topology. Okay, the first thing we've got to do is say, well, is it a metric? And we see that everything is easy except the triangle inequality. The triangle, as usual, the triangle inequality is the only thing you really need to check. Well, for all I, the distance between xi and zi divided by I is less than or equal y and z. Okay, that's just from the triangle inequality on the standard bounded metric. But of course, this has to be less than this sum over here, just by the definition of sup. And this is true. This is true for all I. Therefore, in particular, it's true for the sup. It's going to be less than or equal to that sum. But this, of course, is just the distance between x and z. So it's fairly straightforward to show that it is a metric indeed. Okay, So how do we show these two things are the same? The same way. We show that something in the product topology, something open in the metric topology is also open in the product topology, and something open in the product topology is also open in the metric topology. Go ahead and do that. So U open in metric topology. And let's take a point in our open set. So we can choose, because it's in the metric topology, we can choose, there's going to be a ball centered at X epsilon, which is going to be contained within U, just from the definition of being a metric topology. Then we choose capital N so that 1 on N is less than epsilon. And then we're going to let V equal x1 minus epsilon to x1 plus epsilon cross x2 minus epsilon to x2 plus epsilon, all the way up to xn minus epsilon, xn plus epsilon, and then everything else is just R. And of course, V is a basis element in the product topology. Right, because it's just a finite number of intervals then cross R. But then if we have let Y be a sequence such that the distance between xi and yi divided by I is less than 1 on n, or I bigger than n. So y bar, y is an element of V right there. Then we have this by definition. So the distance between x and y is less than or equal to the maximum of the y2, distance between xn minus yn on n and 1 on n. So this means that y being in V means that, and this is less than epsilon by a choice. So y is indeed an element of V, and it's contained within our BD X. Right, so this basis element can be put inside this basis element, so the basis element of the product inside the basis element in the metric, which is inside, of course, the open in the metric. So that shows that anything open in the metric is also open in the product. Okay. You happy with that? Do the converse direction. This is going very slow. So now we'll let U equal a basis element. In product topology. Again, U alpha I. U alpha. So only got finitely many that are not equal to finitely many which aren't equal to R for alpha equal alpha 1, alpha 2. Okay. That's our standard thing. So what we do now is we've got to choose our epsilon i's greater than 0, but also we want to make sure they're less than or equal to 1, so that xi minus epsilon x alpha I minus epsilon I x alpha I plus epsilon I are contained within U alpha I. And then let epsilon equal the minimum of those epsilon i's. And so if y is an element of the metric ball centered around x, with radius epsilon, call that v, then for all I, we have that the distance between x is x, xi, yi on I is less than the distance between x and y, which is less than epsilon. Okay, I think I've screwed up here. I think actually we can just put everything in the first n factors. Right. So I don't need to worry about alpha i's being anywhere around. We just worry about the first n factors. So for I equal 1 to n, we've got epsilon is less than epsilon I on I. So the distance between xi and yi is less than epsilon I, which is less than 1. So xi minus yi is less than 1. Is less than epsilon I square in the normal, the standard metric in R. So this thing here is in this thing here, and so we've shown that, the converse, that this open is open in the metric. Whew. Okay. So as I said before, if you've got R with an infinite index set, then the box topology is not metrizable, and R to an uncountable index set is not metrizable in the product topology. And as I said before, there are important metric spaces, important subspaces of this set of space of sequences to study. But that really belongs to analysis. Okay, so what can we say about metrics with respect to earlier concepts that we've looked about? So for a subspace, right, if you've got a subspace of a topological space and you look at the restriction of the metric to the subspace, you get a metric for the topology of A. And that's in fact the same as the subspace topology. So subspaces act like you want them to act, and of course the reason for that is, right, if you look at a ball in the metric restricted to A, let's call that A, where A is an element of A, that's going to be the same thing, right, as the ball in the normal metric with A epsilon intersected with A. And that shows you that the metric topology and the subspace topology are going to be the same. Order topologies. So we've seen that some order topologies are metrizable, for example, R, and others are not. What happens if we just add one element to R, infinity? This is no longer metrizable. Okay. So let's get over the fact that the distance from anything to infinity is infinity by just using a bounded metric, using the standard bounded metric. What's the ball centered at infinity of radius 1? Well, it has one element in it. Right. It's got infinity. It can't have any other real numbers in there, right? Because the distance from 3 to infinity is 1 in the standard bounded metric. Right? So that means the singleton infinity is an open set in the metric topology, but it's not going to be an open set in the order topology, because the order topology, the open sets containing infinity look like that. Okay. Hausdorff, we've already mentioned that every metric topology is Hausdorff, just because you can just look at the distance then between them. And then product topology works pretty good, and that's basically what we did before, the same thing. Given no, okay, I shouldn't finish this up. We're already over time. But basically what we did before carries over. We've got lots to say about continuous functions, and that's what we're going to cover next. Ooh.